Okay, good morning, everybody. Getting close to our midterm exam. I wanted to remind everyone that we are going to do an exam review on Tuesday the 9th at 8:30 p.m. I will send out a Zoom link, and the objective at that meeting is to discuss your questions. Okay, so Tuesday at 8:30 p.m., bring your questions. Wednesday, I will tell you what's going to be on the exam. And probably actually I will tell you on Monday the 8th, 2 days beforehand. But as I've said, the exam is going to look like homeworks. So you're going to be asked to do assignment of symmetry. You're going to have to do some molecular orbital stuff. You might do some group theory, maybe a multiplication table, that kind of thing. So it's going to look a lot like the homeworks. Got to get your Vesper going and your resonance structures going and all that.
Sorry.
Go ahead.
I was just wondering how the exam was going to be administered.
We're going to do, this is a good question, actually. I haven't thought about it carefully. I had intended to do it in person over Zoom to limit the amount of time that people have. But I'm not sure how practical that is, I guess, now that I'm realizing everybody needs to be able to print the exam out in order to, well, I guess you could, yeah, I'm not sure how you would do it. You could write it out on paper and then take a picture of your answers. I think I need to think about that a bit more, Samantha, so I'll appreciate the prompt. Ding and I had planned to discuss it after class today. So I will let you know on Wednesday exactly how that's going to happen.
Thanks.
But my intention was to limit it in time. Actually, in the past, I've given exams where I've let people do 24 hours, you know, and maybe in fact it would make sense to take a poll about this. You know, on the one hand, people like to have lots of time to do the exam. On the other, the exam is longer and harder. And, you know, in some ways it might be more useful you to just be under the gun and to get it done in a short period of time. So I'm not sure exactly what I'm going to do there yet, now that I'm unsure how to administer the exam. So I'm going to have to follow up and let you know, and we'll talk about that on Wednesday. Okay, so we're still working our way through molecular orbital diagrams, and last time we talked about pi donors and pi acceptors, and one of the key things that was discussed there, which is a really, really important concept, it was how do you take an electrostatic picture and make it map onto an MO picture? And we talked about an example where you have a pi acceptor, and well, I guess we mostly talked about, we talked about pi acceptors, and we said a pi acceptor is an electron deficient molecule fragment that let me admit these people from the waiting room here. An electron accepting ligand, pi acceptor, is an electron deficient thing. Carbon monoxide is the prototypical example. And being electron deficient means partially positively charged, acidic. it's a place where electrons can go to take a nap. It's a place where electrons can go and rest, right? It's a source of, it's an attractive force that binds the electron, plus likes minus. So a pi acid or a pi accepting ligand is an acidic, positively charged thing that the electrons are attracted to. And when they become associated with that positive charge, they are now stuck to the molecule better, and it's harder to ionize them. If you have a pi donor ligand, now you have an electron pair on your ligand in a pi symmetry orbital, and it donates to the metal. That electron pair is actually held more tightly by the metal by donating to a metal of positive charge. But sometimes the metal has an electron pair as well. And now you're taking two electron pairs and they're butting heads. That's bad. In an MO picture, the electron pair on the ligand drops in energy and the electron pair on the metal goes up in energy. And now you have two filled levels where the electron pair on the metal is high in energy and the one on the ligand is low in energy. So if you consider how easy is it to ionize, that you look at the higher energy orbital and you say, wow, this went up because I put these two electron pairs on top of each other. Now it's easier to pull an electron out of that very bad situation, right? You're putting negative charge on negative charge. The whole thing is more negatively charged, and it's easier to get an electron out of there now. So things like hydrazine, hydroxylamine, you have two lone pairs adjacent to each other with a very short bond distance between them. They are good reductants. They're good nucleophiles because they have a high density of negative charge that molecule wants to get rid of. It's advantageous to pull an electron out of that situation. It's easy to ionize. It's like aniline has a nitrogen adjacent to a benzene ring, and that nitrogen electron pair dumps in there and it makes it easy to pull an electron out. Makes the ring nucleophilic. So when you have a pi donor that dumps electrons onto a system that already has some electrons, you have this electron repulsive interaction. The whole thing goes up in energy. Okay? So you might be surprised to learn that hydrogen peroxide can be a reducing agent. You don't think of it that way. It's a peroxide, right? That's an oxidizer, but it can be reductant. You can make lithium peroxide. That's a great reducing agent. Okay. All right. So we're going to start constructing MO diagrams, complete MO diagrams using group theory, considering pi effects. And we just did a fragment last time. And remember, we compared the sigma only and the pi donor or pi acceptor case. So you can show how the pi effects are a perturbation on the sigma only picture. So we did that for a fragment. Today, we're going to start doing that for an octahedral complex. So let's finish our discussion of Lewis representations from last time. Why are you not responding to me? Huh. Here we go. I'll have to share my screen. Okay. All right, so let's take a look at what is going on. Okay. This thing is not allowing me to write for some reason. Try deleting this thing and starting a new one. I don't know what is going on here.
Are you using an Apple Pencil?
Yeah.
Sometimes like the tip of it gets a little unscrewed.
It's out of battery. I didn't even know these things required a battery. That's not good. Maybe this, I have a second one here. Let's see if this came with some charge. Otherwise, we're going to be doing an interpretive dance here. Oh boy. Well, see how far we can go with this. Probably not very far. I'll charge this one in the meantime. Hey, that's why I got to. Oh, that says 60%. Thank goodness. All right. So, pi acceptors. Now we're still working on those structures here. So we're going to take a look at why are you giving me a hard time? No. This is the one that's so.
Professor, do you have the pencil too, like the second one that is magnetized?
Yeah.
So sometimes, I don't know, do you have automatic software updates? Like, oh, it's working. Never mind. I'm sorry.
Yeah, we'll see what happens here. All right, so we're going to consider this metal carbonyl complex. We've got 2 electron pairs on the metal here, 2 lone pairs on the metal, and I've drawn a neutral fragment overall to make my life easier. Now, one of the resonance structures that you can write is to push one of those electron pairs onto the carbon. Okay, so when we push an electron pair onto the carbon, we're going to push a bond pair off of the carbon and onto the oxygen. When you push the electron pair over to make the bond, now you lose that negative charge. And when you push the bond pair onto the oxygen, now you neutralize the positive charge. So you get a neutral fragment after that. Now you can do this process again. Incidentally, this is one of my favorite resonance structures in all of chemistry. metal carbon triple bond with a single oxide anion hanging out there. Now, when you push that other lone pair over, you get a positive charge on the metal. So you can make, in principle, you can make a triple bond to carbon like that, and that's a good structure for some compounds. Now let's do this with another one. Another classic pi acceptor is trifluorophosphine, phosphorus trifluoride. So now I've drawn, remember, inorganic chemists often don't draw those formal charges. I've drawn them here to be explicit. And so there's a resin structure you can write that looks like this. This is hypervalent, exceeds the octet. You can write another one that looks like this. That would be the hypervalent one. And there are 3 of these. Okay, so pi acceptors you can make multiple bonds with. All right, so we're going to use this picture to do some molecular orbital diagrams. I just want to take a second here to talk about theories of bonding in metal ligand complexes. Instead of saying 6, I'm going to write N. There's sort of a history here. A lot of different people have weighed in on this. One theory of bonding is what's called the valence bond approach. Okay, and this is really a covalent, localized description. Okay, and it's sort of hybridization theory. So if you have a metal ligand complex, like this, you could say that this thing is D2sp3. Okay, that would be the equivalent of sp3 hybridization for methane, right? Mixing in Ds and S's and P's to get to these localized bonds. And notice we've combined 3 atomic orbitals, a total, sorry, of 6 atomic orbitals to get 6 hybrid orbitals out. Another approach is called the crystal field theory. This was really a physicist theory. All interactions are ionic. Can be described like Coulomb interactions. And, you know, this made sense actually in crystals. Where you have a ligand with a negative charge or a partial negative charge, and the metal with a positive charge. And so this picture actually was used to describe metals in crystals. So sapphires and rubies and emeralds, those are alumina crystals that have transition metals doped inside of them. And the transition metals take a site in the crystal that gives it a certain coordination geometry and octahedral. And you end up with all these colors that come from those metal ions. And a lot of physicists spent time trying to understand those spectra using this picture of ionic crystal fields. And then there's the what's called ligand field theory. And this is really the MO approach. Based on the linear combination of atomic orbitals. Okay. So this is really sort of the halfway theory, or there's delocalized bonding. Covalent character. So you have molecular orbitals composed of many components, and you get delocalized states this way, but there is some covalency. So that's kind of how we are going to talk about molecular orbital pictures. And we have been talking about molecular orbital pictures in this way. So now I want to do, we're going to do a MO building exercise again. This is the thing you guys have got to get over the hump on here. So we're going to do a sigma only picture of a octahedral complex. And so here, the ligands could be a bunch of different things. Hydride, ammonia, water, lots of different stuff. And we're going to treat many of these ligands just as simple sigma donors. Okay, and we're going to add pi FX later. But right now we're just doing simple sigma donors. And, you know, lots of different transition metals, but particularly D1 to D6 metals. Are common. So titanium 3+ is a good one. How many electrons, valence electrons, does titanium 3+ have? Well, it starts off with 4. When you make a 3+, you end up with 1 d electron left over. Chromium 3+ has 3 d electrons because it started off with 6. And iron 2+ has 6 d electrons because it started off with 8. And you can know that by looking at the periodic table, or you can know the periodic table and tell me how many valence electrons the transition metal has. You're going to need to be able to do that if you want to be able to analyze many of the problems we're going to do forward, or if you want to go to a lecture, listen to the speaker, and know the electron configuration of the complexes they're working with. You need to know how many d electrons the transition metals have. So you must know the periodic table to be able to do that. And so, you know, you can think about this complex in this way. You've got these 6 ligands around the metal. And each one presents a hybrid orbital. Or you could think about the like 6 hydrides, doesn't matter. Okay, but you've got 6 generic orbitals surrounding the metal. And the character table for octahedral looks something like this. We've got an E, there's 8 C3s, 6 C2s, 6 C4s, 3 C2s, an I, 6 S4, 8 S6, sigma H, and sigma D. Let me give these. And so what we want to know is the reducible representation for these 6 ligand sigma orbitals. Now, how do we do this? How are we going to get this gamma 6 ligand sigma? Can someone tell me the procedure, please? Like a simple one. Go ahead, Rachel.
When you imagine doing the operation on it, the ones that move you don't count, and the ones that don't you do count. So like E would be all 6, whereas like C3, all of them would move, and that would be 0.
Very good. Yeah. So you look to see whether the hybrid orbital on the ligand moves on doing the symmetry operation. And if it moves, it goes off the diagonal and doesn't contribute to the trace. If it doesn't move, it stays on the diagonal and it does contribute to the trace. So where is the C3 that Rachel referred to? It's a shish kebab through one of the faces of the octahedron. So none of the orbitals rest on that axis. And when you spin it 120 degrees, all orbitals move. And so you get a 0. Now there's 2 different kinds of C2 orbitals here. And these 2 here are on the axes of the octahedron. This one is off axis. It's on the edge. Okay, so when you do a C2 operation on the edge, you're going to get back a 0. When you do a C4 operation, that C4 operation basically goes right through here, and it sends this guy to this position, that guy to that position, that guy to that position, and that guy to that position. But these 2 stay put. So this C4 is going to give you a 2. And there are C2s along those same axes where those 2 same orbitals stay put. The inversion operation sits at the center of the octahedron. When you do that, all of the orbitals move. So you get back a 0. And S4 is basically a C4 followed by reflection and so on. What about sigma H?
Stay still.
4 of those orbitals are in the plane. Thank you for answering. Who said that?
Hi, Cheryl.
Cheryl, thank you.
Mm-hmm.
4 of them stay put. And so those guys are going to get a 4. And then sigma D, 2 of them are going to stay put. The two that are along the principal axis. Okay, so there you go. Check to see if the thing moves or not. Now, you can decompose this into irreducible representations using the formula if you want. I like to do it slightly differently. I like to use the character table in a way that's a little simpler. I say, all right, I know that these 6 ligand orbitals overlap with some stuff on the metal. I know they're going to overlap with the s orbital. I know they're going to overlap with the p orbitals. And I know they're going to overlap with the dx squared minus y squared and dz squared orbitals. How do I know that? Experience, but how would you know that?
I don't know if this is the right answer because I've missed a couple classes, but you would check to see if the energy of those different orbitals and their symmetry, like if they're grad or ungrad matched, right? You check to see if like the shape and energy were similar and the symmetry of the orbital were the same. And so they would be able to bond.
Yeah, that's right. So that's the right idea anyway. So the energy piece is about overlap, okay? Interaction strength. But right now we're just talking about symmetry. So the energy piece is not important for deciding what symmetry the orbitals have. To decide what symmetry the orbitals have, I can go look at the character table. So I know what a p orbital is by looking at the character table, because I can look for the x, y, and z functions in the linear column. And that'll tell me where the p orbitals fall in octahedral symmetry. And I know that I should choose my x, y, and z axis along the ligands, and my z axis coincident with the highest symmetry principal axis in the molecule. Okay, octahedral is kind of straightforward. Just put the axis system over the ligands. And that means that px, py, and pz, which align with your axis system, point directly at the ligands. So it's very likely that you're going to get bonding interactions with those orbitals and the ligand orbitals. Okay, so I can say, all right, some component of this representation here is probably going to have p orbital symmetry. And some component is going to have s orbital symmetry. And then some component is going to have the same symmetry as the d orbitals, so that point at the ligands. Okay, so this 6 ligand sigma here breaks down into A1G plus T1U plus EG. And this is S, this is P, and this is dz squared and dx squared minus y squared. So I know dz squared and dx squared minus y squared point at the ligands. And therefore, I expect EG as part of this, one of the irreducible representations that is making up 6 ligand sigma. That's the way to do it. That's the simplest way to do it. Okay. All right. So now there are 3 other d orbitals missing. dxy, dyz, dxz. These guys are T2G in octahedral. You just go look at the table. Character table will show you that. Okay, so these d orbitals didn't get included here. They don't actually overlap with 6 ligand sigma. There's no T2G symmetry here. All right. So let's actually make some salcs for fun here. Combining these guys. So we're going to start off with A1G. So we have our metal, and we have our octahedron. The south looks like that. Now I'm going to draw the bonding combination. So this is the totally in phase combination of ligand orbitals and the metal s orbital. And so the wave function for this 1A1G orbital is going to be some coefficient times 4s plus another coefficient times the ligand sigma orbitals, where the different sigma orbitals add up in a constructive fashion. Okay. T1U. What's T1U? Which orbital is T1U? You can just look back in your notes and check, but I don't have to do that because I see a U there, and I think to myself, what metal orbital basis function has U symmetry? S orbital is U? No, S orbital is G. D orbital? Do D orbitals have inversion symmetry? They do. The lobes are shaded, opposing each other, they're shaded the same, so you can invert them. So D orbitals are of G symmetry. How about a P orbital? P orbitals are of U symmetry because one side is shaded and the other side's not. So when you invert that orbital, it goes from plus on this side to minus. And that inversion makes it U symmetry. So T1U is a P orbital on the metal. So there's the T1U MO. No. Oh darn. Where did you go? Bring all to front. I hate this. Sorry, I have to. Stop sharing because I lost it. Darn. Technical difficulties today. I'm not going to worry about that. So let's do. Now notice this p orbital has a nodal plane, and the MO has a nodal plane, right? The top half of this molecular orbital is shaded. The bottom half is unshaded. So the entire MO has the same symmetry as that p orbital in the middle. Now that nodal plane contains those 4 ligands. And so there's no contribution from the sigma orbital on the nodal plane, because a sigma orbital is like an s orbital. It has maximum amplitude at the nucleus, and it's sitting in that plane. So the plane neutralizes that orbital and doesn't contribute to the MO. So there's a combination of ligand orbitals that's out of phase, or changes sign according to the orientation of that nodal plane. And there are 3 of these. All right, let's do EG. What's EG? We're in d orbital land now. So there's 1/2 of the EG pair. It's hard to draw with these pens, but I think I am getting the hang of it. You can't grab them too tightly. All right, so let's draw this guy out. We've got a EG basis function here. We're doing the x squared minus y squared. That's the one that we're going to choose pointing at the ligands. Other people choose xy pointing at the ligands, and that's just a convention issue. Most people, x squared minus y squared points at the ligands. Your character tables are all going to say that. Okay, x squared minus y squared points at the ligands. We have a 3D x squared minus y squared orbital and its component or coefficient. We have another one composed of sigma 2, 3, 5, and 6, changing sign in an alternating fashion as you go around the thing. And we have another EG orbital based on dz squared, which is going to be now this one is a little bit more complicated. Oopsie, hang on a second here. Now we have sigma 1 and sigma 4, which are the ones that are on the z-axis in the plus configuration. And we have sigma 2, sigma 3, sigma 5, and sigma 6, all in the minus configuration. Those are the ones that interact with the donut. And C8 turns out is greater than C9. Okay, so the lobes along the dumbbell piece of the DZ squared are a little bit larger than the ones that are connected to the donut. And you have 2 ligand orbitals along that axis versus 4 in the middle. So it makes sense that the coefficients would be what they are. All right, and so now those are the salps that make up the orbitals that form bonds, but there's also the T2G set. What do the T2Gs look like? T2Gs point in between the ligands. Okay, these 3 d orbitals have nodal planes that are falling on the ligands. Okay. Okay. So that's really helpful because we're going to do pi effects with d orbitals in a little while. And these T2Gs, which have their lobes in between the ligands, they make pi bonds with all the ligands. Right? Remember, you have a d orbital pointing its 2 lobes at some other p orbital out here that makes a pi bond with them. And that's what you have here. We're going to do this later, but you know, you could imagine a p orbital out here that makes a pi bond. Okay, so T2G doesn't point at the ligands, it's non-bonding. This dx squared minus y squared points at the ligands. The p orbitals point at the ligands. The dz squared points at the ligands. Got to know that. You're going to use that a lot. dz squared points at the ligands, dx squared minus y squared points at the ligands, and T2G does not until you start making pi bonds. Okay. So we're going to do a combination of metal orbitals and 6 ligand orbitals. And we have the T1U orbitals. What are those guys? This is 4P, 4S, 3D. And we have our 6 ligand sigma. Down here. We did that already, e.g. T1U, A1G. And so we're going to make a bond here to these guys. We're going to make a bond to this guy. And we're going to make a bond to the EG, but not to the T2G. Amazing. After all these years, I'm looking at this set of notes and I don't like how this is drawn. I'm going to draw it the way I think it should be drawn now, even though it's wrong in my notes. So we're going to make 3 bonds. We're going to make a bond to some d orbitals of EG symmetry, an s orbital of A1G symmetry, and then the p orbitals. So we got a T1U set of orbitals. There's the 1 T1U on the bottom and the 2 T1U on the top. We have our A1Gs here. That's a bonding combination of this 4s and this 6 ligand sigma A1G. And then we have the EG. That's a combination of the d orbitals of EG symmetry and the 6 ligand sigma of EG symmetry. Okay. Now, right here in the middle, the frontier orbitals. And perhaps you recognize that they are EG and T2G, which may be something you learned in Gen Chem. T2G orbitals are non-bonding. The EG is bonding or anti-bonding in the frontier orbital set. Now, remember, these guys, we're going to describe these as the d orbitals. These ones, of course, are non-bonding, so it's fine to talk about them as being d orbitals. These ones are really anti-bonding with respect to the ligands, but we're going to call them the d orbitals for a lot of our discussion in the rest of the class, because really the energy of these EG orbitals are just perturbed relative to the components. And this EG set down here is the bonding combination. And it's kind of like the ligand orbitals. Okay. So there's a non-bonding set down here and a sigma star set here. This is EG and 1 T2G. And which orbitals make up EG and T2G? And how do you figure that out without looking at your notes?
The EG is going to be whichever are oriented towards the ligand, which is the dz squared and the dx squared minus y squared.
There you go, Alec. Thank you. this is a sigma star orbital here. So we need to have some kind of bonding interaction. We're talking about d orbitals. So we got dz squared and dx squared minus y squared. And Alec knows that because they point at the ligand. So that's how you get an antibonding interaction. Whereas these T2G orbitals point between the ligands. So they're non-bonding in a sigma only picture. So this spacing here is called delta O. Delta O, that spacing is referred to as the octahedral ligand field. What does that mean? The ligand field, the field imposed by the ligands. The field imposed by the ligands perturbs the d orbitals, right? A bunch of negative charges on these ligands surrounding a thing in this octahedral arrangement, and they impinge on the dz squared and the dx squared minus y squared, raising those up in energy. If you put an electron in there, you got to pay a penalty because you've got these ligand negative charges in the way. If you have electrons there, then they really want to get out of there. So you've got ligand negative charges. Now, T2G doesn't really interact with the ligands, doesn't point at them, so they're not perturbed. And so the splitting in energy that you see here is a measure of how perturbed the d orbitals are compared to when they don't interact. It's a great way to measure the strength of the interaction between the ligands and the metal. So this is a useful quantity. And it can be used to predict magnetism, color, a few other things. Okay, so that's why you've heard about it in Gen Chem. So let's take a look at titanium dioxide here. Not titanium dioxide. Let's take a look at the hexaquo ion. I don't have a sample to show you, but its electron configuration let's see here, it's 1 EG 4 times, 2A1G 2 times, 1 T1U 6 times. These are the bonding ligand localized MOs. Sorry, that's not a 2A1G there. That's these are all ones. You've got a 1T2G orbital. That's the non-bonding orbital on titanium. It has 1 electron in it. And then you have this EG level, which has 0 electrons in it. Okay, so the hexaquo ion, we'll just go back and look at our MO diagram for a second here. You get all of these ligand-based orbitals. In the case of the hexaquo ion, they're a bunch of lone pairs from water. Okay, water owns those electrons. And all of these guys are going to be filled with electrons. And then all of the bonding MOs look like the water molecules with the ligands filled. Okay, so these are all like ligand-centric. These ones are sort of titanium-based. And we know for titanium 3+ that it has 1 electron remaining, and it's going to sit here. It's going to sit in this level. It's going to look like a titanium electron. And there's that written out. Bonding one's filled, one electron on the titanium, and then the next highest level is this sigma star EG level that has nothing in it. And this compound has a wonderful lavender color. Try that again. So the extinction coefficient, which is a measure of how probable the electronic transition is, and the depth of the color expressed in units of per molar. Spectrum looks a little bit like this. This guy here is approximately 500 nanometers. And the extinction coefficient of this transition here is 5 per molar per centimeter. That's pretty low. You know, if you get a glass of Malbec, dark purple color, that kind of depth of color is an extinction coefficient that's more like 10,000. This is pale, see-through, like the depth of color in perfume that you might see. So epsilon equal to 5 is small. So this is a pale color. Okay. 500 nanometers is also can be expressed in wave numbers. And can also be expressed in electron volts. Different ways to express that wavelength and energy with 2 different units. This electronic transition arises from promotion of the d electron on titanium from the T2G to the EG level. That's the HOMO-LUMO transition in titanium hexaquo 3+. The D to D transition across delta O. So the energy of the transition tells you about that splitting in the molecular orbital diagram. And delta O really spans a pretty wide range. It can go from 5,000 to 50,000. This is really across from the UV to the near infrared, completely spans the visible spectrum in terms of energies. All right. So just a note to self, 1 electron volt is equal to 1240 nanometers, which is equal to 8,000 inverse centimeters. That's a good thing to remember. 1 electron volt is 1240 nanometers, which is equal to 8,000 inverse centimeters, and this is also equal to 23 kcals per mole. All right, so this color tells you about the delta O, and inorganic chemists are drawn to inorganic chemistry because they like colored stuff. And so they want to know, well, you know, what can we do? But this, my compound changed colors. I added this stuff and it went from pale purple to emerald green, and then it turned red later. That's a common conversation when you're making coordination compounds. It turned black. Oh no, it must have made crap. You know, when I crystallize it, it goes from orange to purple. And then I redissolve it, it becomes orange again. The color tells you a lot about what's happening. I mean, it's by far the easiest way to analyze something. It's a lot quicker than taking an NMR spectrum. So the delta O is really useful. And so people spend a lot of time figuring out how delta O is changing. Delta O increases as the charge on the complex, or really on the central metal, becomes more positive. Okay, the ligands are negatively charged or partially negatively charged. They donate electrons to the metal. The more positive that metal gets, the more they are pushing and pulling together. And that gives rise to larger energy splittings. Increasing positive charge pulls in the ligands tightly and raises the energy of the antibonding level. You know, you can sort of do a test where when the ligands are here and you put an electron in, what's the ionization energy? If you pull the ligands in more tightly and you put an electron in, what's the ionization energy? Okay, more tightly and the harder they talk to each other, the more difficult it is to squeeze an electron in there. Increasing positive charge, however, also stabilizes lone pairs on the metal. So both things are happening, but delta O gives rise to a larger splitting overall when the positive charge increases. All right, it also goes up as you go down. So now we're talking about a period in the transition metal series. So nickel, palladium, platinum, delta O increases. Okay, bonding with the 5D transition metals is greater. The bonds are stronger than 4D or than 3D. So the delta O's are larger for 5D transition metals. Okay, this delta O tells you about the bond strength. It tells you about the intensity of the interaction, and it's greater for a 5D metal. 5D metals make stronger bonds than 3D metals do. So the delta O's are larger. And just a reminder, this is the opposite of the main group, right? You go down in the main group, bonding gets weaker. All right, let's do an example here. We're going to look at some ammonia complexes here. 3+ ions, cobalt to iridium. So these metal 3+ ions have 60 electrons, because cobalt, rhodium, and iridium are adjacent to nickel, palladium, platinum. Nickel, palladium, platinum. Platinum defines the end of the transition metals. Platinum is D10. Nickel, palladium, platinum are D10. So cobalt, rhodium, and iridium are one row over. Those are D9. So we have a 3+ ion that gives us 60 electrons remaining. And so you have 1 T2G 6 EG 0. Neat and tidy. So we have the metal here. And we're going to write out the delta O's for these. Cobalt, rhodium, and iridium are 22,900 inverse centimeters. 39,100 and 41. You go from cobalt to rhodium to iridium, the delta O increases. The bonds are stronger for iridium than cobalt. Delta O depends upon the ligand as well. Let's take a look at this fun compound here. Cobalt 3 hexacyanocobalt 3. This compound is 3-. Its delta O is 33,500. So quite a bit larger than the 22,900 of the cobalt 3 hexaquo ion. Now, a couple of different things have happened here. It's 3- instead of 3+. Okay, because you got all these negatively charged ligands, the cyanide anion, surrounding that cobalt 3. And so you might say, all right, well, 3- should narrow the delta O, because normally with the negative charge, now the ligands kind of get pushed away. The molecule wants to relieve some of that tension. And so the pushing the ligands away makes the splitting lower. But the other issue here is that delta O is larger because of pi interactions. And cyanide is a strong sigma donor compared to water. Water is sort of a wimpy donor. It's not very basic. Cyanide is more basic than water. And it's a carbon atom with a lone pair on it. That makes it a good sigma donor. Those two things increase delta O. Stronger donor and a pi acceptor. Okay, that's a fine place to stop. So next time we're going to pick this up again, and then we're going to add some pi effects to our octahedral diagram. And then we're almost out of the woods and all that stuff. Not quite, but yeah. another difficult set of problems to go. I'm going to stop here. And it's 12:55, so if people want to head out, I'll see you again on Wednesday with clarity about the exam, a list of topics and how it's going to be administered. And for anybody that wants to stick around and ask questions, I'm happy to spend some time with you. So otherwise, I'll see you on Wednesday.